Swayam Prabha. Digital India. Educated India.
Welcome to this lecture number 6 on zones of aeration and saturation, followed by the aquifers and the characteristics classification. So, in the previous lecture we discussed about the groundwater column, and specifically of course, we briefly dealt about this zone of saturation, which is below the water table, and zone of aeration, which is above the water table. And we also discussed about how in the zone of aeration, how the water is held, which is basically in the intermediate zone, which is the Vadose water. And here, so this water is held by hygroscopy and capillary action. So, here because of this the attraction between the soil or the rock particles as well as the water. So, the water is held, the water which is not moving is held by these two actions, and the capillary rise is we also saw the expression for the capillary rise, which is given by this 2 sigma into cos theta divided by r into, that is the specific gravity. So, here now let us continue. Before this one, I would like to mention, so essentially, so in this Vadose water, water held by hygroscopic and capillary action. And here, so in this groundwater, so water is held by gravitational action. Okay. And continuing with this the expression for this capillary rise. So, here suppose this is a capillary tube, which is basically a narrow tube. This is a center line, and the diameter of the tube is given by 2 r, and so this is the surface tension force, which is measured as force per unit length, and this is the angle theta, and then this is the water surface, the meniscus, and so this is the that is the liquid, in this case it is water with specific weight gamma, and this theta is the angle of contact which I have mentioned here, and say for if we further simplify, so this so the surface tension which is measured as the force per unit length, so generally it has a value of say 0.074. So, this is grams per centimeter. Of course, so this has to be multiplied by the acceleration due to gravity, that is 9.81, and then this specific weight of water, again this is 1 gram per cubic centimeter, again it has to be multiplied by the, so this multiplied by g. So, this g is the gravitational acceleration, which is say 9.81 meter per second square, and this theta is approximately equal to 0 degree for water and clean glass. Same thing can be assumed in the for water and soil also. Same can be assumed for water and soil also. Therefore, the expression for this capillary rise H, so it reduces to say 0.15 divided by R. Okay. So, as you can see from this one, the capillary rise H, which determines the height of the capillary zone, is inversely proportional to the size of the capillary pores, that is the radius of the capillary pores, that is basically here we are approximating the pores into the equivalent circular shapes and then taking its radius. So, this H as this the equivalent the circular pore radius gets reduced. So, the height of the capillary rise increases, and here it is mentioned that say for different samples, that is the say the material, grain size in millimeter, then capillary rise in centimeter. So, here on the lowest level, where the capillary rise is as low as just 2.5 centimeter, we have this fine gravel whose grain size is that is 0.05 to 0.2. .02 okay, and further as we go. So, this is next is coarse sand. Of course, there are intermediate formations are there. So, here coarse sand for which it is a 1, the grain size is 1, that is 0.1 to 0.5 millimeter, and it has a capillary rise of 13.5 centimeter, and then I am sorry, I made a mistake here. So, this has just let me correct this one. So, this is grain size is 2 to 5. And coarse sand, the grain size is 0.5 to 1. Let me rewrite this again. So, this is the material grain size in millimeter, then capillary rise in centimeter. See, on the coarsest one, we have say fine gravel. The grain size is say 2 to 5 millimeter, and the capillary rise, because this is too large grain size. So, therefore, the pore size is also too large. So, therefore, the capillary rise is as small as say 2.5 centimeter, followed by very coarse sand. The grain size is 1 to 2 millimeter, and the capillary rise is say 6.5 centimeter. Still, let us go to still smaller as one, that is a coarse sand, where the grain size is say 0.5 to 1 millimeter, and then the capillary rise increases as the grain size is getting reduced, and correspondingly the pore size also gets reduced. So, this is 13.5 centimeter. Then the medium sand has a grain size of 0.2 to 0.5, and the capillary rise of say 24.6 centimeter, I am sorry. Then followed by say fine sand, the grain size is say 0.1 to 0.2, and the capillary rise gets further increased to say 42.8 centimeter. Then it is the silt, which has a grain size of 0.05 to 0.1 millimeter. The capillary rise increases to 105.5 centimeter, and lastly it is the fine silt. It has a grain size of say 0.02 to 0.05, and the capillary rise is as high as 200 centimeter. So, you can imagine say how the grain size as the material gets finer and finer in terms of its grain size. So, the capillary rise increases, and this has been, so source is a study by Lohmann. Okay. And now, let me also represent here the distribution of water in a coarse sand. Water distribution in coarse sand above water table. After drainage. So, here suppose this is the this is the moisture content. So, this is the soil moisture content as percentage, and then this is a height above water table in centimeter, and here say let us say this is so this is 20 and then this is 40, and here let us say this is $20, $40. So, here this variation is, it will be something like this. So, this is the, so this represents porosity, and here this represents capillary zone, and above this represents the intermediate zone. So, in the capillary zone, just at the water table level, so the moisture content is exactly equal to the porosity, and as we go above the water table, so the moisture content goes on decreasing, as you can see from here, and so when we reach this intermediate zone, so the moisture content, it represents only the hygroscopic water. So, whereas here, so here you can say this is the hygroscopic component, and then this is the moisture content held by capillary action, and then this is the moisture content held by hygroscopic action. So, therefore, so in the intermediate zone, it is entirely the water is held by hygroscopic action, whereas in the capillary zone water is held by hygroscopic and capillary action. So, you can see how it varies, and say, so just at the water table level, just above the water table. So, almost all the pores are filled with this moisture, soil moisture, and then as we go higher and higher, it is only those pores which are continuous. So, they will be filled with water, and as we reach this intermediate zone. So, it is only the hygroscopic water, which is the water held by the force of attraction between the spaces, the void spaces, as well as the air, as well as the soil or rock particles, and then the water. So, this is how for in the zone of saturation the water is held entirely by gravity, and that is for all the zone below the water table, and as we go above at the water table. So, this the water is held by hygroscopic as well as capillary action, and as we reach the intermediate zone. So, the number of pores which contain soil moisture gets reduced, only those continuous pores. So, they first of all, for this capillary action they must have a very small size, and then so through which this capillary rise takes place due to the force of attraction between the soil or rock particle and water due to the surface tension force, and above that in the intermediate zone it is entirely by the intermolecular attraction between the soil moisture, the air voids, as well as the soil or rock particles. So, now let us consider and this water content which is held by various actions, whether it is the hygroscopic action in the intermediate vadose zone, or the hygroscopic as well as capillary action in the capillary zone, both in the zone of aeration and further below in the zone of saturation by gravitational acceleration. So, this moisture can be measured by various methods, such as the gravimetric method as well as the other the tensiometers and so on. And the same thing here we can mention here by a tensiometer. Basically, it just pulls. So, this water which is held in the that is the measurement of soil moisture. So, this is by gravimetric method in which we take the weight measurements and also say by tensiometer. So, in this tensiometer, suppose this is the soil column, and here So, this is the tensiometer. So, this is the porous cup, and then this is the unsaturated soil, and here so this is the suction head. Which is essentially the water held by the molecular attraction between water, air particles as well as soil particles. So, now let us come to what is known as the available water or available moisture content. So, here suppose I represent, so this is the soil moisture, and here, so this is 0. So, the maximum soil moisture, so this is a soil moisture content which can be, which is possible, is denoted as the field capacity. So, this moisture content, let me represent this as MC. So, this is the field capacity moisture content. So, this field capacity is essentially the maximum possible water which can be held in this zone of aeration, and also the minimum, this is amount of soil moisture corresponds to, so this is the permanent wilting point, or simply it is known as the wilting point. Moisture content. And of course, there is also an intermediate, this is known as the optimum moisture content. Or say OMC. So, here, so essentially, so this field capacity is the amount of water which is held in a soil after wetting and after drainage has become negligible. So, generally it is after say 2 days of drainage. So, the after 2 days of keeping it for draining. So, all the water which is generally goes out through drainage, that gets drained out, and then the moisture content which remains in that soil sample or soil or rock sample is the one which represents the field capacity moisture content, and the total amount of moisture is the volume of that is the known as the field capacity. And similarly, so this wilting point is the moisture content, it represents the moisture content wherein the plants start wilting. That means, say below this wilting point, so the all the water all the moisture, it is held by only molecular attraction between moisture or water particles as well as air and soil or rock particles. So, it is not given away by the soil. So, therefore, plants cannot extract any water by capillary action. So, the plants start wilting or drying. So, these drying plants, so further, so they die. So, this difference between the field capacity moisture content and then the permanent wilting point. So, this is known as available moisture content. And similarly, the difference between the field capacity and optimum moisture content, which is slightly higher than the permanent wilting point. So, this is known as the readily available moisture content. So, essentially, so all the irrigation, so they depend upon this readily available moisture, which can be easily extracted by the plants through capillary action. So, therefore, in this irrigation what is done is, so as soon as the soil moisture gets depleted to this optimum moisture content level, so then one irrigation supply is given. So, then the moisture content increases to field capacity moisture content level, and then further again by the due to plants metabolic activity, due to evapotranspiration as well as evaporation, the soil moisture gets gradually decreased, and again when it reaches this optimum moisture content, then the next irrigation is given. So, like this, so this is how the process of irrigation continues. Now, let us come to the moisture content in the zone of this one. So, this is available moisture. So, here, so this is in the zone of aeration. Okay. Now, let us come to the zone of saturation, which is the now let us come to available water in the zone of saturation. Again here, so in the zone of saturation, so most of the water is held by this zone of this is gravity action. Of course, very small amount is held by this hygroscopic action. So, here let us define say two terms, which is the specific retention So, if we denote this as SR, so this is the ratio of the volume of water which is retained in soil against gravity after saturation divided by the total volume. So, this VR is the water volume retained in soil after saturation against gravity. And this V is the total soil or rock volume. And let us also define another terminology here, that is the specific yield, which is denoted by SY. So, here, so this is equal to V y divided by V, where again V is the total soil or rock volume, and this V y is the volume of water drained, and obviously, so this is by gravity. Okay. And so this N, which is the porosity, of course, few authors in the previous class, I think I represented this by alpha, and few authors they use the notation N. So, this is equal to the specific retention plus specific yield. So, this is a very important relationship between porosity and specific yield as well as specific retention. And here, so essentially, so if I represent, so this is the water table. So, the water retained above water table is known as the field capacity. Water, here you can say that is moisture retained in the zone of aeration. So, here you can say the, let me use the word maximum water, and here, so this is the, and below this it is the water retained. So, this is water retained corresponding to the specific retention SR, maximum water retained in the zone of saturation. So, essentially this field capacity as well as the water retained, so they represent the same water content, while the field capacity represents the water, the maximum water retained in the zone of aeration, wherein all the pores are saturated, while the water retained represents the maximum water retained in the zone of saturation, and obviously, so this is corresponding to SR. So, this here you can say this is, and both are against gravity. Okay. So, like this, so the essentially this field capacity as well as water retained, so they represent the water which can be retained to a maximum extent in the zone of aeration as well as zone of saturation. So, now let me also represent here, so the, and as this groundwater is one. So, our objective is to harness or to extract groundwater as much as possible. So, therefore, the specific yield is more important to us, and here suppose I represent on a scale the specific yield expressed as percentage. So, here on the lowest level, say this is 10, 20, 30, 40, and in the highest this one, that is around say 44, we have peat, which is basically the vegetative matter which has decomposed, and then the lowest specific yield is observed in clay, which is so peat, it has 44%, and this clay which has the minimum, which is 3%, and in between we have say the dune sand, %, and we have say medium sand, which has say 28%, and we have say coarse gravel, %, and we have sandstone, %, and we have limestone, 14%, and we have silt here with generally this one. Okay. So, these are some of the typical values of the specific yield in different materials, ranging from the minimum of 3% in found in clays and the maximum of 44% found in around 44% found in peat. So, in between we have so this silt, limestone, then sandstone, coarse gravel, medium sand, dune sand, okay, and of course, few more. So, this is the variation of specific yield in different soil or rock formations. Now, let us come to the aquifers, their classification, characteristics and classification. So, these aquifers are essentially these water bearing layers. So, here you can say in this so typically we can say this above this limestone, all these rock or soil formations, they represent aquifers, and below this limestone all the soil or rock formations, they represent either aquitards or aquicludes or aquifuges, which you discussed in the previous class, in the previous lecture. So, here I would like to draw your attention to a schematic cross section representing the various aquifers. So, these are the impervious. So, this is the impervious strata, so this is the recharge area, so this is the ground level, and here I would like to represent the water table or the piezometric surface. So, this is the water table, and this is piezometric surface, which represents basically the energy. And here, after this recharge through different forms of precipitation, so this soil moisture, the water moves in this this is known as the confined aquifer, which is essentially confined at the top as well as bottom by confining layer. So, this is the confining layer. And here, suppose we drill a well here, which penetrates all the way up to the confined aquifer, and here this one we may find, so this is water table. So, this well is penetrating through the all the way, and here this is the confined aquifer, and then here this is the unconfined aquifer, also known as let me write here. So, this unconfined aquifer that is water table aquifer. So, this unconfined aquifer represents the topmost aquifer which has only the one confining layer at the bottom, whereas its top surface represents the water table which is subject to, which is undulating, and it is depending upon the slope, the areas of recharge, discharge and pumping and other factors. And in this case, so now let us come to this well which has been dug in the, which has been drilled in the area, in the land area which is below the piezometric surface, and it penetrates all the way up to the confined aquifer. And here the total, so this piezometric surface represents the energy, the total energy at that level for this depth up all the way up to the confined aquifer. So, therefore, here the well starts oozing out water corresponding to this piezometric surface, and such a well is known as a flowing well. So, here the water gushes out of the well on its own. So, no artificial pumping is required. And on the other hand, suppose we drill a well which penetrates only the unconfined aquifer. In this case, the surface, the water surface will be corresponding to the water table at that location, and so therefore, this well which penetrates only the unconfined aquifer is known as the water table well. And on the other hand, suppose we drill another well which penetrates through the confined as well as unconfined aquifer. So, here the water table corresponds to this one, and the piezometric surface, and this well is known as artesian well. So, this confined aquifer is also referred to as artesian aquifer, which is also known as pressure aquifer. Okay. So, there are three types of wells: the flowing well, the water table well, as well as the artesian well. So, in the flowing well, the water gushes out on its naturally by because of the ground surface being below the piezometric surface there, whereas in the water table well as well as the artesian well, so the water surface will be below the corresponding to the water table or the piezometric surface, and this artesian well, it draws from both the confined as well as unconfined aquifer at the bottom as well as unconfined aquifer at the top. So, we will stop here and we will continue further our I will continue our discussion in the next lecture. Thank you.